For over 100 years, the speed of light has been treated as the final wall of the universe, a limit no ship, engine, or civilization could ever cross. But scientists are now exploring a shocking possibility. Faster than light travel may not mean moving the spacecraft faster, but making space itself move around it. Before we continue, take 1 second to like and subscribe because this idea could change the future of space travel. Get ready? We begin now. Push harder and you go faster. That's not a theory. That's a lived experience, written into the body before anyone ever opened a physics textbook. A child on a bicycle figures it out in an afternoon. Pedal harder, go faster, add a motor, go faster still, strap a rocket engine to the back, and now you're talking. The entire arc of human transportation from the first wooden wheel dragging through mud to the Saturn. 5 tearing through the atmosphere at 25,000 miles per hour follows the exact same logic. More force, more speed, simple, linear, obvious. So when people hear that the speed of light is a barrier, the natural assumption is that it's an engineering problem. We don't have engines powerful enough yet. We don't have the right fuel. We haven't figured out the right design. Give it a few centuries, give it 1,000 years. Humanity has a way of solving problems that look impossible from the outside. We thought powered flight was a fantasy. We thought reaching the moon was science fiction. We thought splitting the atom was a philosopher's daydream. And then we did all three within a single lifetime. So the speed of light, 300,000 kilometers per second. Surely that's just the next mountain to climb. Except it isn't. And here's where the floor drops out. At 99% of the speed of light, something happens that no amount of engineering can fix. Time on the spacecraft slows down by a factor of 7. Not metaphorically, not as a rounding error. Literally, a clock on that ship ticks 7 times slower than a clock sitting still on Earth. If you left on a mission and came back after what felt like 1 year aboard the vessel, 7 years would have passed back home. Your children would be older. Your friends would have moved on. The world would have changed in ways you didn't witness. But that's not even the part that breaks the intuition. The part that breaks it is this. The effective mass of the spacecraft increases by a factor of 7 as well, at 99% of the speed of light. Your ship doesn't just feel heavier, it is heavier. In every meaningful physical sense, it resists acceleration more. It demands more energy just to maintain its current speed, let alone increase it. To accelerate 1 single kilogram of matter to 99%. The speed of light requires energy equivalent to approximately 6 billion tons of TNT, not to travel somewhere, not to do anything useful at the destination, just to get 1 kilogram moving that fast. 6 billion tons of TNT. For 1 kilogram, a standard automobile weighs roughly 1,500 kilograms. A small crewed spacecraft, stripped to the absolute minimum, might weigh tens of thousands of kilograms. Scale the math and the numbers become numbers that language struggles to hold. This is not a fuel problem. This is not an engine design problem. This is the universe itself changing the rules of the game as you approach the finish line. The technical term is relativistic mass increase, derived directly from the Lorentz factor in Einstein's special relativity. But the technical term doesn't capture the feeling of it. A better image. Imagine your spaceship is being slowly turned to stone. Every meter per second you add, another layer of concrete pours itself over the hull. At low speeds, the layer is so thin you can't feel it. At 90% of the speed of light, the layer is noticeable. At 99%, the ship weighs 7 times what it did at rest. It moves like something that has forgotten how to move. And time. Time does the opposite. It thins out, stretches. Each second on board becomes 7 seconds in the outside universe. The clock doesn't slow because something is wrong with the mechanism, there's no malfunction to repair. It slows because time itself, in that reference frame, actually flows at a different rate. This is not a thought experiment. This is a measured, confirmed, experimentally verified fact. GPS satellites have to account for time dilation constantly. Without the correction, GPS systems would drift by several kilometers per day. The effect is real, it is quantified, and it scales brutally as you approach the speed of light. So here's the structure of what's actually happening. You add energy, the ship gets heavier. A heavier ship requires even more energy to accelerate further. That additional energy makes it heavier still. You're not climbing a hill. You're climbing a hill that grows steeper with every step, where the weight you're carrying increases every time you move forward. The universe isn't blocking you with a wall. It's billing you at an ever-escalating rate for every fraction of a percent you inch closer to the limit. Which raises an uncomfortable question. If adding more energy makes the object heavier rather than faster, what exactly are we burning the fuel for? The answer, at relativistic speeds, is that you're paying an increasingly extortionate toll just to maintain the illusion of progress. You're pouring in energy, and the universe is pocketing most of it as mass, handing back only the thinnest sliver of additional velocity. It's the worst exchange rate in the cosmos. The good news, if you somehow got aboard a ship traveling at 99% of the speed of light, you would age more slowly than anyone left behind. Your body would experience less time. By some measures, that's the closest thing to a fountain of youth the laws of physics permit. The bad news, you would need the entire energy output of the sun across 1 million years just to purchase the ticket for that journey. Not for a round trip. One way, 1 kilogram. That's the admission price the universe charges. And 99% is still not enough. Not even close to enough. 99% of the speed of light is still not the speed of light. The gap between 99% and 100%, a gap that sounds trivially small, is in fact an infinite chasm. You can inch toward it forever and never close it. The closer you get, the harder the universe pushes back, and it does so with a precision that is not accidental, not arbitrary, and not fixable with better technology. The speed of light is not the top speed in a race where faster engines win. It is the structural boundary of what it means to be matter existing in spacetime at all. But that number at 99% is only the gentle warning at 99.999%. The universe stops warning you entirely and sends the bill straight to your face. From 99%, push further, 99.9, 99.99, 99.999% of the speed of light. Each decimal feels like a small step. In reality, each decimal is a cliff. At 99.999% of the speed of light, the Lorentz factor, the multiplier that governs both time dilation and relativistic mass, surpasses 700, not 700. The ship that weighed 10,000 kilograms at rest now behaves, for the purposes of momentum and energy, as though it weighs 7 million kilograms. The time dilation is equally savage. 1 year aboard the vessel corresponds to over 700 years outside. You could leave Earth, travel for what feels like a decade of your personal experience, and return to find that 7,000 years have elapsed. Every person you ever knew would be dust. Every institution, every language, every civilization you recognized, gone, replaced, forgotten, rebuilt, and forgotten again. And this is still not the speed of light. To reach exactly 100%, to close that last impossible sliver of a gap, the Lorentz factor doesn't reach a large number. It reaches infinity. The energy required doesn't become very large. It becomes infinite. Not more than we currently produce. Not more than our solar system generates. Infinite. as in more than the total energy content of the observable universe, which itself spans 93 billion light-years in diameter and contains an estimated 2 trillion galaxies, each with hundreds of billions of stars. All of that energy, every photon, every nuclear reaction, every quantum of electromagnetic radiation across the entire observable cosmos would not be enough to accelerate a single kilogram of matter to exactly the speed of light. This is not an engineering limitation. This is a mathematical theorem, a proof. The same kind of certainty as saying you cannot find the largest prime number, or that two parallel lines in flat geometry will never intersect. It is not that we lack the tools. It is that the destination does not exist within the structure of the mathematics that describes our universe. Most people, when they hear this, cycle through a predictable response. First disbelief, then, well, maybe there's an exception. Then, what about wormholes? Then, almost inevitably, but what if you just went faster than light anyway? What's the actual worst case? The actual worst case is not a large explosion. It's not a spacecraft torn apart by stress. The actual worst case is the complete logical disintegration of cause and effect across the entire universe. Here's why. Imagine you are aboard a hypothetical ship that has exceeded the speed of light. You send a message back to Earth. That message traveling at the speed of light is now slower than you are, which means from certain reference frames, moving at different velocities relative to yours, that message arrives at Earth before you sent it, not almost before. Before. The mathematics of special relativity, when you apply them to faster than light information transfer, produces negative time intervals in some reference frames. The message arrives in the past. Now, make it concrete. You are 10 seconds away from a catastrophic accident. Someone on Earth using your faster-than-light message sends you a warning. You receive it 10 seconds before the accident occurs. You avoid the accident. The accident never happens. But if the accident never happens, the warning was never needed. If the warning was never sent, you never received it. If you never received it, you didn't avoid the accident. If you didn't avoid it, it happened. If it happened, the warning was sent. If the warning was sent, you received it and avoided it. The loop has no exit. This is not a paradox in the loose, casual sense of the word. A quirky, logical puzzle to argue about over coffee. This is a structural contradiction in the fabric of causality itself. Cause and effect, the sequence that says A must happen before B if A caused B, is not merely a convention humans invented to make sense of the world. It is the foundation on which every law of physics is constructed. Every equation in chemistry, every mechanism in biology, every interaction between particles, every transfer of energy, all of it assumes that causes precede their effects. Remove that assumption, and you don't get a universe with strange new rules. You get a universe with no coherent rules at all. Physics doesn't bend, it dissolves. The entire structure, from the quantum interactions that hold atoms together to the gravitational dynamics of galaxy clusters, rests on this single scaffolding. Time moves forward. Causes produce effects that come after. The universe is internally consistent because of this, and only because of this. You're thinking it. Right now, maybe there's an exception. Maybe in some exotic corner of the cosmos, causality breaks down locally, and the rest of the universe doesn't notice. There is no such corner. The moment faster than light information transfer is permitted anywhere in the universe, even once, even briefly, even at a scale too small to observe directly. The mathematical framework of special relativity allows you to construct reference frames in which that transfer happened in the past. And a transfer of information into the past is a closed causal loop. Every closed causal loop is a logical contradiction. Every logical contradiction in physics means the model is wrong or the scenario is impossible. Since the model has been confirmed to extraordinary precision across a century of experiments, the scenario is impossible. This is what separates the speed of light from every other challenge humanity has ever faced. Climbing a mountain is hard but solvable. Building a rocket is complex but achievable. Splitting an atom was once called impossible and then was done within 40 years. But exceeding the speed of light doesn't require better technology. It requires the universe to abandon the logical structure that makes it a universe at all. The speed of light is not the ceiling of a room you can raise with enough effort. It is the definition of the room. The room cannot be larger than its own definition. And yet Einstein, the man who proved all of this, also left behind something else, buried inside his own equations. Not an error, not an oversight, a door that he may not have realized he was building. But Einstein, the man who built this ceiling, also left a crack in the wall. Not in his calculations, but in the very heart of the greatest theory he ever wrote. Space is empty. That's the assumption almost everyone carries, without ever questioning it. Not empty in the sense of mostly nothing. Empty in the deeper sense of being a neutral, featureless container, a stage, a backdrop. The universe happens inside space, the way a play happens inside a theater. The theater doesn't participate. It doesn't flex, doesn't bend, doesn't have opinions about what occurs within it. It just holds the performance and stays out of the way. Newton built his entire system on this picture, and it worked magnificently for 2 centuries. Absolute space, his term. His framework was the fixed, unchanging reference frame against which all motion could be measured. Objects moved through it. Gravity acted across it. Time ticked uniformly within it, independent of everything else, indifferent to mass, indifferent to speed. The image was clean, intuitive, and enormously productive. It predicted the motion of planets, cannonballs, pendulums, and ocean tides with an accuracy that seemed, for a very long time, to settle the question permanently. The intuition it produced is still the default setting of the human mind. Walk outside tonight and look up. What you feel instinctively is that the stars exist inside a vast, dark, unchanging emptiness, that space is simply the absence of things. The room that everything else inhabits. Ask anyone on the street what space is. They will describe a container. Permanent, passive, something that holds the universe the way a jar holds water, without itself being part of what's happening inside. That picture is wrong. Not approximately wrong. Not wrong only in extreme conditions. Wrong in a way so foundational that once you genuinely absorb the correction, the old picture becomes impossible to recover. You cannot unknow it. In 1915, after a decade of work that he later described as the most intense intellectual struggle of his life, Einstein published the general theory of relativity. What it said about space was a category correction of the deepest kind. Space is not a stage. It is not a container. Space is a physical entity with its own geometry, its own behavior, its own capacity to respond to what exists within it. Mass and energy curve spacetime. A massive object doesn't just sit in space, it deforms the space around it, the way a heavy iron ball deforms a stretched rubber sheet. And that deformation is gravity, not a force transmitted invisibly across a vacuum, but the geometry of spacetime itself guiding the motion of everything that moves through it. The immediate confirmation came from our own solar system. Mercury's orbit precesses its elliptical path, rotates slowly around the sun over time at a rate that Newtonian mechanics had never been able to fully account for. 43 arcseconds per century of unexplained drift, stubbornly sitting in the data for decades. General relativity calculated it exactly, without adjustment, without approximation. Then, in 1919, during a total solar eclipse, the British astronomer Arthur Eddington photographed starlight passing near the sun. The light bent. It bent by exactly the angle Einstein had predicted. The stage, it turned out, was made of something real, and that something responded to mass by curving. But curvature is only the beginning. If space can curve, it can also stretch. It can expand. And here is where the universe stops being a philosophical curiosity and becomes something viscerally strange. Galaxies located more than approximately 4.4 billion light-years away from us are receding faster than the speed of light. Not rushing through space at superluminal velocities that remains forbidden by special relativity, but being carried away as the space between us and them expands. The distance is growing faster than light can cross it, and this is not a violation of any law. It is completely, rigorously consistent with general relativity, because the prohibition in special relativity is narrowly specific. Matter cannot move through space faster than light. The theory says nothing, not one word about how fast space itself is permitted to expand. That distinction is not a technicality, it is structural. The two prohibitions live in different theories that govern different things. The clearest way to feel the difference: picture an ant on the surface of a balloon. The ant has a fixed maximum crawling speed, its own biological limit, absolute and non-negotiable. Now inflate the balloon rapidly enough, and 2 points on the surface move apart faster than the ant can ever travel between them, no matter how hard it tries. The ant isn't cheating. It isn't breaking any rule. It's moving at full speed, in full compliance with everything that governs ant motion. It's just that the surface it's traveling on is expanding faster than its legs can compensate. The ant's local speed limit is entirely respected. The balloon, indifferent and vast, expands at whatever rate it expands. That is the universe. You are the ant, space is the balloon, and right now, in every direction you point a telescope, the balloon is being inflated. This isn't a metaphor constructed for pedagogical convenience. It is the literal structure of what cosmologists measure when they observe distant galaxies. Their recession velocities are not velocities through space. They are velocities of space, scaling linearly with distance according to the Hubble constant. The further away an object is, the faster it recedes. At a certain distance, the recession velocity equals the speed of light exactly. Beyond that threshold, it exceeds it, not by a little, by arbitrarily large amounts, for objects arbitrarily far beyond the boundary. Everything past that boundary is unreachable, not because the journey would take too long, not because the fuel cost is too high, but because no signal, no matter how fast, no matter what it's made of, can outrun the expansion that's carrying the destination away. The gap grows faster than any gap closing is physically possible. And if that seems like the extreme end of strangeness, consider what happened in the very first moments after the Big Bang. During the period cosmologists call cosmic inflation, which occurred at approximately 10 to the power of negative 32 seconds after the origin of the universe, a span of time so inconceivably brief that the word moment fails entirely to capture it, space expanded at a rate that dwarfs everything else in the history of the cosmos. A region of space smaller than a single proton, smaller than any particle we have ever detected, inflated to roughly the size of a golf ball in that unmeasurable instant. Points that had been separated by subatomic distances found themselves light years apart. The expansion velocity during inflation was not merely faster than light, it was faster than light by factors that stagger calculation. Potentially, quadrillions of times the speed of light, and none of it violated a single physical law. Because no matter was moving through space, space itself was the thing changing. The metric, the mathematical structure that defines what distance means, was rewriting itself. The distinction between the two theories, stated plainly: special relativity governs the motion of matter and energy within spacetime. General relativity governs the behavior of spacetime itself. They operate on different objects. The speed of light barrier is absolute within special relativity's domain. It simply does not appear as a constraint in the equations describing how space expands, contracts, or curves. The two are not in conflict. They govern different things. And the gap between their domains is precisely where the loophole lives. So the question reframes completely. If the limit applies to matter moving through space, but not to space moving on its own terms, what happens if you stop trying to push matter through space and instead engineer space to move around you? What if the ship doesn't move and the destination comes closer instead? What if you don't accelerate? You reshape the geometry. Right now, the light from hundreds of billions of galaxies will never reach your eyes. Not because space is too wide, not because you lack a fast enough ship, because space is running away faster than light can chase it. The universe is contracting around you, tightening the boundary of what is knowable, what is reachable, what is real in any practical sense, 1 second at a time, silently, without asking permission. And that loophole isn't a desktop theory right now. The universe is using it every single second, right in front of us, at a scale no telescope can fully capture. There is a boundary drawn around every observer in the universe. Most people have never heard of it. It doesn't appear in news headlines or high school textbooks, but it is arguably one of the most consequential facts in all of cosmology. It's called the Hubble horizon, sometimes the Hubble radius, and it marks the precise distance at which the recession velocity of space equals exactly the speed of light. On one side of that line, the universe you can, in principle, interact with. On the other side, a permanent, physical, irrevocable silence. That boundary sits approximately 13.8 billion light-years away from us, in every direction simultaneously. 13.8 billion light-years. The number matches the age of the universe in years, and that alignment is not coincidence. It emerges directly from the expansion history of spacetime. More importantly, this figure is not an estimate drawn from incomplete theory. It is a measurement. The European Space Agency's Planck satellite, which completed its primary mission mapping the cosmic microwave background, the faint thermal glow left over from when the universe was roughly 380,000 years old, produced data of extraordinary resolution. Temperature fluctuations in that ancient light, smaller than 100,000th of a degree, encoded the geometry, composition, and expansion rate of the entire observable universe. From that data, cosmologists extracted the Hubble constant, the curvature of spacetime, the ratio of dark matter to ordinary matter to dark energy, and from all of that, the precise location of the horizon beyond which expansion has permanently severed any possible causal contact with us. Beyond 13.8 billion light-years, nothing reaches us. Not light emitted today, not a signal sent a billion years from now, not anything. Because the expansion is not merely continuing, it is accelerating. Dark energy, the term physicists use for the observed accelerating expansion, whose underlying nature remains genuinely unknown, is pushing the universe apart at an increasing rate. Galaxies that sit near the edge of our horizon today will, over the next hundreds of billions of years, be carried past it entirely. The sphere of the universe we can ever interact with is shrinking, not the universe itself, the accessible portion. The region with which any exchange of information, energy, or matter remains physically possible is becoming smaller with every passing second, and nothing about our technological trajectory will change that. The Planck data also confirmed something else, quieter but equally striking. The universe is geometrically flat to a precision of within a few tenths of a percent, not curved like the surface of a sphere, where parallel lines eventually meet, not saddle-shaped, where they diverge. Flat, which in cosmological terms implies that the universe extends, potentially without limit, beyond the boundary we can observe. The total universe, the one that actually exists, rather than the one we have access to, may be unimaginably larger than the observable portion, Some models suggest it could be at least 10 to the power of 23 times larger than what our instruments can detect. Others suggest it may be genuinely infinite. All of it unreachable. All of it expanding away. Sit with that for a moment. Most of what exists will never be known. Not because we haven't built the right telescope. Not because we haven't waited long enough. Because the physics of expansion has drawn a permanent line and nothing crosses it from the other side. Now pivot. Because what this implies is not despair. It's a reframing of the entire question. If space itself can move, if it carries galaxies away at superluminal recession velocities without breaking a single rule of physics, then superluminal motion is not prohibited. It is happening right now, continuously, at cosmic scale. The universe has been doing it since approximately 10 to the power of negative 32 seconds after the Big Bang and has not paused once. The prohibition in special relativity is real and absolute, but it governs matter moving through space. The motion of space itself exists in a different category entirely, one where no speed limit has ever been written, which means the question transforms. Not is faster than light travel possible? That framing already concedes too much to the wrong model. The better question, the one with actual physical traction, is this: can the expansion of space be made to work for a traveler rather than against one? Can space-time geometry be arranged so that a region of space, the region containing a spacecraft, moves toward a destination, while the craft itself remains locally at rest? This is precisely the question that a Mexican theoretical physicist named Miguel Alcubierre asked in 1994. He was not an experimentalist. He did not have a laboratory, a particle accelerator, or a government grant for propulsion research. He had the field equations of general relativity, a willingness to work backward from a desired outcome, and the intellectual courage to ask a question that most of his colleagues considered either frivolous or hopeless. The technique is sometimes called reverse engineering, a space-time metric. Standard physics starts with a physical configuration and asks what behavior results. Alcubierre inverted it entirely. He started with the behavior he wanted: a spacecraft traveling from Earth to a star 4 light years away and arriving in a time shorter than 4 years, as measured by both the crew and observers on Earth, and then asked Einstein's equations what distribution of mass and energy would produce a space-time geometry capable of that. He fed the destination into the mathematics and waited for the mathematics to describe the road. And the equations answered him. Clearly, consistently, without internal contradiction. The answer was strange in its elegance. Not a more powerful rocket, not a tunnel through space-time, not a shortcut through a higher dimension. Something far more subtle: a bubble. A localized region of flat space-time surrounding the ship, with space compressed in front of it and expanded behind it, riding a wave of geometric distortion toward its destination, while the ship inside experiences no acceleration, no time dilation, no relativistic mass increase, nothing. From the inside, nothing happens. From the outside, the bubble moves. Turns out the universe doesn't prohibit faster than light travel. It only prohibits you from doing it. The universe itself does it every second without effort or apology. And the man who found the answer didn't invent a new engine. He didn't build a reactor. He simply sat down, took Einstein's own equations, and asked in reverse, if I wanted to get there, what would space-time need to look like? Every spacecraft in the popular imagination looks roughly the same. Engines at the back, glowing white or orange or blue depending on the franchise. The hull shuddering under acceleration, crew pressed back into their seats, faces distorted by G-force, veins visible at the temples, fuel burning, thrust building, the ship lunging forward through the dark. This is the model encoded into every science fiction film ever made, from the Millennium Falcon tearing into hyperspace to the Endurance grinding through the gravitational pull of Gargantua in Interstellar. And it's not just fiction, it's the only model of spaceflight that humanity has ever actually practiced. Every rocket ever launched, from the first Sputnik to the Saturn V to the Falcon Heavy, operates on exactly this principle. You want to go somewhere, you point the engines, you burn the fuel, you push the mass. Physics rewards the push with velocity. The harder you push, the faster you go. That model has served us magnificently within the solar system. It got 12 human beings to the surface of the moon and back. It flung the Voyager probes past the edge of the heliosphere. It placed instruments in orbit around Jupiter, Saturn, Mars, Mercury, Dome, and Pluto. The logic is clean and satisfying. Motion comes from force. Force comes from fuel. And the problem of getting anywhere faster reduces to the engineering problem of carrying more fuel and burning it more efficiently. Carry that logic to interstellar travel, and it collapses completely. Not because the engineering is hard, though it is, brutally so, but because the fundamental premise fails. As parts 1 and 2 made clear, matter moving through space runs into a wall that fuel cannot break. The faster you go, the heavier you become, and the more energy you pour in, the worse the exchange rate gets. The model of push and accelerate hits a structural limit built into the fabric of space-time itself. Miguel Alcubierre, a Mexican theoretical physicist working in 1994, did not try to push harder. He abandoned the model entirely. What he designed was not an engine. It was not a propulsion system in any conventional sense. It was a geometry, specifically a configuration of space-time, a bubble within which a spacecraft would sit perfectly, completely, utterly still. No engines firing, no thrust, no G-force pressing the crew into their seats, no relativistic mass increase threatening to drain the energy budget of a civilization. The ship itself would not move at all. Instead, space would move around it. The concept demands a specific kind of mental reorientation. Space in front of the bubble contracts. The distance between the bubble and its destination shrinks not because the ship traveled across that distance, but because the distance itself became smaller. Simultaneously, space behind the bubble expands, generating an effective push. The bubble rides the resulting gradient of space-time geometry the way a surfer rides a wave, not swimming through the water, not fighting the ocean, standing on a board while the ocean's own dynamics carry everything forward. The airport moving walkway is another way to see it. You stand still. Your feet don't move. The belt beneath you moves, and you arrive at the gate faster than walking would have taken you, without any effort on your part. Now imagine the walkway is space-time itself, and the gate is 4 light-years away. The mechanism doesn't violate special relativity. This is the critical detail. Special relativity prohibits matter from moving through space faster than light. Inside the Alcubierre bubble, the ship is in a locally flat region of space-time. Its local velocity, measured within its own immediate neighborhood, is exactly 0. It is at rest. Special relativity governs local motion, and locally, nothing is moving. The bubble itself is what moves, carried by the geometry of space-time. And general relativity, which governs the behavior of space-time geometry, places no speed limit on that. The theoretical consequence is extraordinary. If you can create and sustain the bubble, it can, in principle, move at any speed, 10 times the speed of light, 100 times, 1,000 times. The mathematics does not break. No internal inconsistency appears. The equations remain satisfied. A journey to Alpha Centauri, 4 light-years away, could take days or hours rather than 40,000 years at conventional speeds. A journey to the Andromeda Galaxy, 2.5 million light-years away, a distance that would require 2.5 million years of travel at the speed of light, becomes in principle, a finite mission, the crew inside experiences none of the costs that relativity normally imposes. Time dilation. Absent, because the ship isn't moving relativistically through space. Relativistic mass increase. Absent, for the same reason. G-force during acceleration. Absent, because the bubble's geometry changes while the ship remains inertial. The passengers would feel nothing unusual. They would sit in normal gravity, age at the normal rate, eat breakfast, read a book, look out the window, and somehow be traveling faster than any light signal could follow. From outside, the bubble moves. From inside, nothing does. The destination approaches not because the ship went to it, but because space-time geometry made the distance between them smaller. You're wondering if it's that elegant. Why hasn't anyone built it? That is exactly the right question, and the answer to it will make you genuinely uncertain whether the universe is indifferent or whether it is, in some strange sense, actively uncooperative. The mathematics answered that question perfectly, almost frighteningly. So, and the moment the answer appeared, it arrived with a condition that no laboratory on Earth has ever produced. Alcubierre published his paper in 1994 in Classical and Quantum Gravity, one of the most respected peer-reviewed journals in theoretical physics. It was not rejected. It was not dismissed as speculation dressed in equations. It passed peer review. It was published. It entered the scientific literature as a legitimate, mathematically consistent solution to Einstein's field equations, a proposed space-time metric, describing a configuration in which apparent superluminal travel becomes physically realizable without violating the foundational laws of special relativity. That alone is historically significant in a way that's easy to underestimate. For the entire 20th century, prior to 1994, faster-than-light travel had existed in one of two categories: science fiction, or vague theorizing that nobody could write down precisely. Alcubierre put it in a third category. He wrote it down rigorously, in the language of differential geometry and tensor calculus, the same mathematical language Einstein had used to describe the curvature of spacetime 80 years earlier. The warp drive was no longer a dream. It was a solution, a specific, testable, internally consistent solution to the most powerful gravitational theory ever constructed. The reason Einstein's field equations allowed this is worth pausing on. Those equations are, in a precise technical sense, remarkably permissive. They describe a relationship between the geometry of spacetime on one side and the distribution of mass and energy on the other. What Alcubierre did, and this is the reverse engineering technique that Part 4 introduced, was specify the geometry first, then ask the equations to tell him what distribution of energy and matter would produce it. It is the mathematical equivalent of describing your desired destination in exhaustive detail and asking the GPS to compute the route backward from there. The equations obliged. They produced a specific energy-matter distribution that would generate the warp bubble metric. The calculation was self-consistent. No contradictions appeared. The mathematics did not break down, did not produce infinities in the wrong places, did not flag any internal violation. By the standards of theoretical physics, the Alcubierre drive was a valid result. This was the first time in the history of science that a mechanism for apparent faster-than-light travel had been described by equations that were not invented for the purpose, but rather derived from established theory. Not a new theory proposed to allow it, not a modification of known physics designed to permit it. The same equations Einstein wrote in 1915 applied in a new way, produced it naturally. That is a different kind of legitimacy entirely. For nearly 2 decades, the paper sat in the literature cited, discussed, occasionally updated, but broadly considered an interesting mathematical curiosity with no practical path forward. Then, in 2012, Harold Sonny White, a physicist and engineer at NASA's Johnson Space Center, took a fresh look at the energy requirements and found a significant optimization. Alcubierre's original design specified a spherical bubble, a perfect sphere of modified spacetime, surrounding the ship. White's analysis showed that altering the bubble's geometry from a sphere to a toroidal shape, something like a donut or a ring wrapping around the ship rather than enclosing it entirely, dramatically reduced the energy required to sustain it, not by a small margin, by potentially many orders of magnitude. White also showed that oscillating the bubble's wall thickness, rather than holding it constant, introduced further efficiencies. The numbers that had previously seemed cosmologically absurd began to look, while still enormous, at least directionally more approachable. White's work generated considerable attention, both within the scientific community and beyond it. NASA itself announced a low-level experimental program to investigate whether any measurable space-time distortion could be detected in laboratory conditions, using a device called the White-Jude Warp Field Interferometer. The results were inconclusive, and the energy effects involved were many orders of magnitude below any practical significance. But the point was philosophical as much as experimental. A national space agency was officially and on record conducting research into warp field mechanics. The conversation had moved. Alcubierre essentially solved the interstellar travel problem on a Tuesday afternoon, and then immediately discovered he needed something that didn't exist to implement it, which is, if you think about it, exactly what it feels like to be a great theorist. The mathematics is pristine. The universe, however, has opinions. Because when you follow the energy-matter distribution that the equations specified when you ask, not just what geometry do we want, but what physical substance do we need to produce that geometry, the answer that comes back is something that most physicists would have told you before 1994 probably couldn't exist at any useful scale. Something that sits at the absolute boundary of what quantum mechanics permits. Something that has been measured, confirmed, real, and then immediately shown to be available only in quantities so vanishingly small that using it for propulsion would be like trying to power a transatlantic flight on the static electricity from a balloon rubbed against a wool sweater. The mathematics doesn't ask for more fuel. It doesn't ask for a bigger reactor or a denser energy source. It asks for something with a property that ordinary matter and energy simply do not possess, a property so counterintuitive that its existence required the full machinery of quantum field theory to even establish, and whose practical limitations make the relativistic mass problem from parts 1 and 2 look almost manageable by comparison. What the mathematics demands is not plutonium, not antimatter, not an artificial black hole. It demands something whose very concept violates the most basic physical intuition. Most people carry energy with a negative value. What the mathematics demands isn't plutonium, isn't antimatter, isn't an artificial black hole. It demands something whose very concept violates the most basic physical intuition: energy with a negative value. Energy is always positive. That statement feels so obvious, it barely qualifies as a statement. It's more like background noise, the kind of assumption so deeply embedded in everyday experience that questioning it never occurs to anyone. Gasoline has energy. Sunlight has energy. A charged battery has energy. A spinning flywheel has energy. Every form of energy you can name, point to, measure, or use to do something useful in the world carries a positive value. You can add energies together. You can convert them between forms. You can store them, release them, direct them, but the number on the label is always greater than 0. This is not something most people learned from a textbook. It's something absorbed from birth, from the experience of living in a world where things burn, shine, move, and heat up. Energy is the capacity to do work, and doing work is always a positive act. The idea of negative energy with a value below 0 sounds about as meaningful as negative apples, or a temperature colder then absolute zero. It doesn't parse? It sounds like the kind of thing a science fiction writer invents when they need a hand wave badly enough. We'll use negative energy. Sure. And while you're at it, grab some negative apples from the negative refrigerator. Except quantum mechanics disagrees. Firmly, experimentally, reproducibly, negative energy exists, not as a theoretical placeholder, not as a mathematical convenience that cancels out in the final answer, but as a physically real phenomenon that has been measured in a laboratory, verified by independent groups, and incorporated into the design of actual working technology. The confirmation came through the Casimir effect, first measured with precision by Steve Lamoureux at Yale University in 1997. The setup is deceptively simple. Two uncharged, perfectly conducting metal plates, placed extraordinarily close together, separated by gaps on the order of micrometers, or smaller inside a vacuum. Classical physics predicts nothing interesting happens. There is no charge, no current, no magnetic field, no obvious reason for any force to appear between the plates. The vacuum between them is empty. But quantum field theory says the vacuum is not empty. It is a seething, fluctuating sea of virtual particle pairs, particles and antiparticles that pop into existence and annihilate each other so rapidly that they cannot be directly observed, but whose collective effect on the energy of space is real and measurable. In open space, these fluctuations occur at all wavelengths simultaneously. Between the two plates, however, only fluctuations whose wavelengths fit within the gap can exist longer. Wavelengths are excluded by the geometry. The result is that the energy density of the vacuum between the plates is slightly lower than the energy density of the vacuum outside them, lower than the baseline vacuum, lower, in the relevant sense, than zero. That deficit, that region of below baseline energy density, is negative energy, and it produces a measurable, real physical force. The two plates attract each other, drawn together by the pressure difference between the richer vacuum outside and the depleted vacuum between them. Lamoureux measured this force to within 5% of the theoretical prediction. Subsequent experiments refined the measurement further. The Casimir effect is not a curiosity. It is a confirmed feature of physical reality, and its implications show up in the engineering of microelectromechanical systems. The tiny machines built at scales where quantum vacuum fluctuations are large enough to matter. When engineers design MEMS devices, the microscale sensors inside smartphones, medical instruments, and aerospace systems, they have to account for Casimir forces as a real mechanical factor. Negative energy is not philosophy. It is an engineering consideration. So negative energy exists. The Alcubierre metric requires it. The connection seems promising. The reason the warp bubble needs negative energy specifically comes down to the geometry of what it has to accomplish. Ordinary gravity produced by positive energy and positive mass curves. Space-time in one direction. It focuses geodesics, the paths that light and matter naturally follow through space-time, drawing them inward. Every massive object does this. The sun curves the geodesics around it toward itself. The Earth does the same. This focusing effect is what gravity looks like in geometric terms. To compress space in front of the warp bubble, you need the opposite. You need something that defocuses geodesics, that pushes the natural paths of light and matter outward rather than inward. Ordinary matter cannot do this. Ordinary energy cannot do this. The only thing the equations permit to produce this effect is negative energy density. Think of it this way. Normal gravity is a stretched spring, always pulling things toward its center, always contracting the geometry around it. Negative energy is a compressed spring it pushes outward, expanding the geometry away from it. To bend space-time in both directions, simultaneously compressing it ahead of the bubble and expanding it behind you need both springs. One you can build from ordinary matter. The other requires something the universe produces only in the narrowest, most grudging quantities imaginable. How much negative energy does the warp bubble need, Alcubierre's original calculation, for a bubble roughly 100 meters in diameter, traveling at the speed of light, produced a figure equivalent to the mass energy of Jupiter. Not Jupiter's output, not Jupiter's fuel reserves. Jupiter itself, the entire planet, converted entirely into negative energy and concentrated at the bubble wall. Jupiter has a mass of approximately 1.9 times 10 to the power of 27 kilograms. Converting that to energy via Einstein's mass energy equivalence gives a number so large that no unit commonly used in engineering or even astronomy conveys it cleanly. And every gram of it would need to be negative. The Casimir effect, by comparison, produces negative energy densities on the order of microjoules millionths of a single joule across areas of a few square centimeters. The gap between what the Casimir effect delivers and what the warp bubble requires is not a gap that engineering closes. It is not a gap that civilization-scale energy production closes. It is the gap between a single candle flame and the sun, and that comparison is not rhetorical exaggeration. It is close to arithmetically accurate. The Casimir effect generates negative energy at roughly 1/1,000,000th of a joule per square centimeter under optimal laboratory conditions. The warp bubble requires negative energy equivalent to the mass energy of an entire gas giant. The ratio between those two numbers is so extreme that describing it as a gap between a candle and the sun actually undersells the problem by dozens of orders of magnitude. You have confirmed that the ingredient exists. You have confirmed that the universe produces it. You have confirmed that quantum mechanics permits it. What the universe has absolutely not confirmed is that you can ever collect enough of it to matter. Worse still, negative energy isn't just scarce. The universe has its own standing law to ensure you can never accumulate enough of it. No matter how many millions of years you spend trying, Harold White's optimization in 2012 looked, on the surface, like a breakthrough. By changing the geometry of the warp bubble from a sphere to a toroidal shape, a ring encircling the spacecraft rather than a sphere enclosing it, and by introducing oscillations in the wall thickness of the bubble, White's calculations showed a dramatic reduction in the negative energy requirement. The original Alcubierre figure, equivalent to the mass energy of Jupiter, dropped precipitously. In White's revised framework, the negative energy required fell to roughly equivalent to the mass of the Voyager 1 spacecraft, approximately 700 kilograms. 700 kilograms instead of a gas giant. That sounds, at first encounter, like the difference between impossible and merely very difficult. The kind of progress that should generate excitement. And to White's credit, it did. NASA assigned resources to preliminary experimental investigation. The numbers had moved from cosmologically absurd to merely astronomically challenging. But pause on what the figure actually means. 700 kilograms of negative energy. Not 700 kilograms of hydrogen fuel. Not 700 kilograms of antimatter, which would itself be the most energy-dense substance ever produced and requires the entire output of the world's particle accelerators for years to make a single microgram. 700 kilograms of negative energy, a substance the universe produces spontaneously only in submicroscopic quantities, in the gaps between metal plates held nanometers apart, in amounts measured in millionths of a joule. The optimization reduced the requirement by many orders of magnitude. The requirement remains so far beyond any conceivable production capacity that the improvement, while mathematically real, offers no practical path forward. And then, 1 year after Alcubierre's original paper, the situation became worse in a direction nobody had fully anticipated. In 1995, Lawrence Ford and Thomas Roman published a set of results now known as the Ford-Roman quantum inequalities. Ford had been working on the theoretical constraints governing negative energy since the 1970s, And what he and Roman formalized was a fundamental limitation built into quantum field theory itself, not a technological limitation, not an engineering constraint, but a law, a theorem, a statement about what the quantum vacuum will and will not permit. The constraint runs as follows. The quantum vacuum does allow local regions of negative energy density. The Casimir effect proves this. But the vacuum enforces a strict accounting rule: the larger the magnitude of the negative energy density you want to create, the shorter the time interval over which it can exist. And the relationship between the two is not linear. It is inverse and severe. If you want negative energy twice as dense, you can sustain it for roughly 1/4 the time. Push for 10 times the density, and you get 1/100th the duration. The more intense the negative energy, the more violently and immediately the vacuum demands repayment in positive energy, with an interest rate that scales so steeply that the net effect is always, without exception, a wash or worse. The physical picture is this. The quantum vacuum behaves like a lender who will extend you credit, but only under terms that guarantee you cannot profit from the loan. You can borrow negative energy from the vacuum. The vacuum dips below its baseline to accommodate you, but it snaps back with a positive energy pulse so quickly and of such magnitude that you cannot extract any lasting benefit. The negative energy exists, flickers, and is immediately canceled by an equal or greater positive energy surge. The net result averages to 0 or above every time, without exception. Think of it as a credit card with an interest rate of 1,000,000% per second. The bank will lend you the money. It will appear in your account. You will technically hold it for a measurable, real, non-zero interval of time. But the debt accrues so fast, and the repayment is demanded so immediately, that you will never get to spend it on anything. Before you can walk to the register, the account is not just empty, it's deeply negative in the other direction. Now apply this to the warp bubble. A spacecraft traveling at 10 times the speed of light toward Alpha Centauri would take roughly 5 months to arrive. During those 5 months, the warp bubble must maintain its negative energy distribution continuously, uniformly, at the wall of the bubble, across a region of space large enough to enclose a spacecraft. That means sustaining a large, dense, macroscopic concentration of negative energy for approximately 150 days. Under the Ford-Roman quantum inequalities, the permitted duration for negative energy of the magnitude and spatial extent required is not 150 days. It is not 150 seconds. It is not 150 microseconds. The permitted duration falls so far below any operationally useful timescale that describing it in human units requires scientific notation with deeply negative exponents. Quantum mechanics is essentially telling you, yes, you can borrow the negative energy. You have to return it in 10 to the power of negative 44 seconds. That is the Planck time, the smallest meaningful unit of time that current physics recognizes. The scale at which spacetime itself becomes quantum and continuous description breaks down entirely. The universe is offering you a loan with a repayment window smaller than the universe can even describe. That is, to put it charitably, somewhat impractical for an interstellar voyage. The Ford-Roman inequalities don't merely make warp drives difficult. They establish a structural incompatibility between the timescales required for warp travel and the timescales over which the quantum vacuum permits the necessary energy conditions. It is not a gap that better engineering closes, because the constraint doesn't come from the engineering. It comes from quantum field theory, the same framework that predicted the Casimir effect, the Lamb shift, and the anomalous magnetic moment of the electron to 11 decimal places of precision. The framework is not wrong. The constraint is not negotiable. But just suppose that some future physics, some synthesis of quantum mechanics and general relativity that we don't yet possess, found a way around the Ford-Roman constraints. Suppose the negative energy problem dissolved entirely. Suppose someone somehow built the bubble would still kill you, not from the energy problem, not from a containment failure, from something far simpler, far more fundamental, and far more total. You would be completely, permanently, inescapably blind. But suppose you somehow solved the negative energy problem. Suppose you found a way to sustain it. The warp bubble would still kill you, not from an explosion, not from energy leakage, but from a reason that leaves you with no options at all. You would be blind. Every vehicle ever built by human hands shares one non-negotiable feature. Not an engine, not fuel, not even wheels or wings. Control. The ability to change direction, reduce speed, stop entirely, respond to what's ahead. A bicycle without brakes is not a bicycle. It's a hazard. A car without a steering wheel is not a car. It's a projectile. The entire history of transportation engineering, from the first rudder on a Phoenician merchant vessel to the fly-by-wire systems on a modern commercial aircraft, is fundamentally a history of control systems. Making things go fast is the easy part. Making them go where you want, when you want, and stop when you need to, that is the actual problem that engineers spend their careers solving. Space travel is no different. Every crewed spacecraft ever launched carried with it thrusters for attitude control, retro rockets for deceleration, communication systems for relaying commands from ground controllers, and onboard computers running guidance algorithms continuously updating trajectory. The Apollo capsule had manual override controls. The space shuttle had hydraulic actuators on every control surface. The International Space Station performs regular orbital adjustment burns. Nobody who has ever designed a spacecraft has had to ask whether the vehicle would be steerable, because of course it would be. That's what a spacecraft is, a controlled vehicle operating in space. Carry that assumption into the warp bubble, and it shatters completely. A warp bubble traveling faster than light does not merely make steering difficult, it makes steering physically impossible, not as an engineering challenge, but as a consequence of the same physics that permits the bubble to exist at all. The mechanism is this. A bubble moving at superluminal velocity creates an event horizon around the spacecraft. Not a metaphorical horizon, a genuine, relativistic event horizon. A boundary beyond which no signal, no light, no information of any kind can propagate fast enough to reach the front wall of the bubble. Think carefully about what that means for the people inside. Any command the crew wants to send to the bubble's boundary, any instruction to alter course, reduce speed, expand or contract the geometry, must travel from inside the ship outward to the wall of the bubble. That signal, whatever form it takes, travels at the speed of light at most. But the front wall of the bubble is moving away from the interior faster than light. The signal chases the wall and never catches it. The command is issued and never arrives. The crew can think whatever they want, decide whatever they want, input whatever they want into whatever control system they built, and none of it reaches the boundary in time to change anything. You cannot steer, cannot brake, cannot signal, cannot alter trajectory by a single degree, cannot avoid anything in the path ahead. The ship is not blind in the casual sense of having poor sensors or limited visibility. It is blind in the absolute physical sense that no information about the outside universe can reach the crew faster than the wall is moving away, and no information from the crew can reach the wall at all. The event horizon is a one-way membrane, and it surrounds you completely. The closest physical analogy is the interior of a black hole. Inverted, inside a black hole's event horizon, nothing travels outward fast enough to escape light included. Inside a superluminal warp bubble, the situation at the forward boundary is structurally identical. Nothing from inside travels forward fast enough to influence the wall. The geometry traps your agency as effectively as the geometry of a black hole traps your body. Driving blindfolded at 1,000 kilometers per hour captures part of it, but only part. At least the blindfolded driver can turn the wheel. The hands can reach the steering column. The mechanical linkage between intention and control surface remains intact. In the warp bubble, the linkage itself is severed by physics. You could reach for the controls. You could turn them. The signal they generate would travel at the speed of light toward the bubble wall and fall short. Every time, by exactly the margin that the wall's velocity exceeds light. The intention never arrives. The wheel spins in a room that cannot hear it. This is not a design flaw that a sufficiently clever engineer can correct. There is no communication technology that transmits information faster than light. That prohibition is the same prohibition that makes the warp bubble theoretically interesting in the first place. Any system that could control the bubble would need to send signals faster than light to reach the bubble's boundary, which requires violating the very constraint the bubble was designed to circumvent. The problem is not a gap in engineering. It is a logical closure. The thing that makes the bubble work is the same thing that makes the bubble uncontrollable. So the spacecraft, your spacecraft, crewed with people, launched with hope, aimed at a star becomes a bullet, not a guided projectile, not a smart munition with terminal guidance. A bullet in the oldest, simplest sense, an object with a trajectory and no further say in where that trajectory ends. It goes where it was pointed when it launched. It does not deviate. It does not stop. It does not respond to what it finds along the way. Stars, planets, debris fields, other spacecraft, none of it matters. The bubble neither knows nor cares. You are moving faster than light toward a planetary system that might harbor life, and you cannot see it coming, cannot slow down, cannot steer around it, cannot warn anyone. That trajectory belongs to physics now, not to you. Who answers for that? And blindness is only the first problem. The second transforms your exploration vessel into something no civilization anywhere in the universe would want to see coming toward them. The warp bubble is extraordinarily fragile. Not fragile in the sense that it requires careful handling or precise maintenance. Fragile in the sense that the quantum vacuum itself is continuously trying to destroy it, and succeeding requires an ongoing battle against fluctuations that cannot be suppressed, predicted, or eliminated. A 2009 study published in Physical Review Letters by Stefano Finazzi, Stefano Liberati, and Carlos Barceló examined the stability of the Alcubierre metric in detail. Their conclusion was unambiguous. The warp bubble is quantum mechanically unstable. The geometry that defines the bubble, the sharp gradient between compressed space at the front and expanded space at the rear, mediated by the bubble wall, creates conditions at the boundary where quantum vacuum fluctuations are not merely present, but amplified. Each fluctuation that arises at the wall, rather than averaging out or dissipating, feeds back into the system in a way that increases the next fluctuation. Positive feedback. The kind of instability that engineers design systems specifically to avoid, because once it begins, it accelerates until the system fails catastrophically. The image that captures it tried to balance a pencil upright on its sharpened point. Mathematically, there exists an exact vertical position where the pencil would stand indefinitely perfectly balanced. Center of mass directly above the point of contact. Net torque exactly zero. That position is a valid solution to the equations of classical mechanics. But in practice, no pencil has ever stood that way for more than a fraction of a second. Because any infinitesimal perturbation, a breath of air, a vibration transmitted through the table, a quantum fluctuation in the thermal environment nudges the pencil off that perfect balance point, and gravity immediately amplifies the deviation. The further it leans, the stronger the torque, pulling it further. The solution exists. The stability does not. The warp bubble is that pencil, and the quantum vacuum breathes constantly. But the instability, as catastrophic as it would be for the crew, is almost secondary to what the bubble does to everything else, to the space it moves through, and, most devastatingly, to the destination it arrives at. Interstellar space is not empty. This is worth stating clearly because the word vacuum implies otherwise. The interstellar medium contains, on average, approximately 1 hydrogen atom per cubic centimeter. That density is vanishingly thin by any terrestrial standard. A vacuum chamber on Earth holds far more matter, but space is large, and a ship traveling across light years sweeps through an enormous volume. Beyond hydrogen, the interstellar medium contains helium, trace amounts of heavier elements, dust grains, molecular clouds of varying density, the cosmic microwave background radiation permeating every cubic centimeter of the universe, neutrinos streaming outward from every star, and high-energy cosmic ray particles traveling at near light speed themselves. None of this matter sits quietly outside the bubble and lets it pass. The bubble wall, moving at superluminal velocity, sweeps through this material continuously. The geometry at the front wall where space is being compressed acts as a collector. Particles and radiation that would ordinarily pass through the region are instead captured by the advancing geometry and piled up against the forward surface of the bubble. They accumulate there, compressed, energized by the motion, unable to escape forward because the bubble is moving faster than they can travel. The longer the journey, the more material accumulates. Across interstellar distances, the layer thickens steadily, building into a concentrated shell of compressed matter and radiation, riding the bubble wall like the bow wave of a ship cutting through water. Except the energy scales involved are not nautical. They are astronomical. A 2021 paper by Alexei Bobrik and Johnny Martire, published in Classical and Quantum Gravity, examined the energy dynamics of the warp bubble across a complete journey. The finding regarding deceleration was stark. When the bubble slows and eventually collapses at its destination, the accumulated material at the forward wall is released. All of it, simultaneously, in the form of a directed burst of gamma radiation and high-energy particles. The energy released in this event scales with both the speed of travel and the distance covered. For an interstellar journey at meaningful warp velocities, even modest ones by science fiction standards, the energy released upon arrival is sufficient to sterilize the destination planetary system entirely. Not damage it, not disrupt it, sterilize it. Every planet, every moon, every body in the system swept by radiation intense enough to strip atmospheres and destroy any complex chemistry that might exist on any surface. The monstrous irony sits right at the center of the whole enterprise. The entire motivation for building a warp drive is exploration, reaching other stars to find planets, perhaps find life, perhaps find neighbors in a universe that feels achingly empty. Every interstellar mission in the history of human imagination has carried this hope as its deepest justification. And the warp drive, if it worked, would make every mission a weapon, not by accident, not by malfunction, but by physics. The bow wave is not a side effect that better design eliminates. It is a consequence of the geometry itself. The bubble collects, the collapse releases. There is no version of the journey that doesn't end with an explosion at the destination. We would send a warp ship to Alpha Centauri to search for life, and the moment it arrived, it would deliver a gamma ray burst as a greeting. First contact, expressed as total annihilation, the kind of impression that tends to be permanent. But if you followed all of this and still believed these problems could be engineered away with sufficiently advanced technology, you haven't yet met the final layer of the defense network the universe built to stop any civilization that tries to break the speed of light. Every problem has a solution. That belief is not naive. It is the working assumption that has driven the entire history of science and engineering forward. When a problem appears, you study it, isolate its cause, design a fix, test the fix, refine it, and move on. The process is iterative but directional. Progress is real. Each solved problem opens the path to the next one. History backs this up without ambiguity. Heavier-than-air flight was declared physically impossible by serious thinkers well into the 19th century. And then the Wright brothers flew at Kitty Hawk in 1903. 12 seconds the first time, 59 seconds by the fourth attempt that same morning. Splitting the atom was considered the province of fantasy until Ernest Rutherford did it in 1917, and within 3 decades, the energy released by that split had reshaped the world. Reaching the moon was dismissed as science fiction well into the 1950s, and then Neil Armstrong's boot pressed into lunar dust in July of 1969, less than a decade after Kennedy made it a national commitment. The pattern is consistent enough that it functions almost as a law given sufficient time, resources, and intelligence. The obstacles fall. So when physicists catalog the problems with the Alcubierre drive negative energy requirements, quantum instability, the event horizon control problem, the gamma ray weapon at arrival, the natural response from a certain kind of mind was fine? Solve them one by one. Replace the negative energy with positive energy. Redesign the bubble geometry until it stabilizes. Find a way to signal through the wall. Engineer a dispersal mechanism at the destination. Problems are problems. That's what they're for. Several groups took exactly this approach. The mathematics of general relativity, being as permissive as it is, does allow warp metric solutions constructed entirely from positive energy. You do not strictly need negative energy to write down a space-time metric that moves a region of space from one place to another at superluminal velocity. The equations will accept a positive energy configuration and produce a valid warp solution. The math clears. No internal contradiction appears on the page. But when you follow that solution all the way to its physical implications, when you ask not just, does this metric exist, but how does it come to exist, and when, and from what prior state, the universe produces an answer that is not a technical obstacle. It is a logical impossibility of a different and deeper kind. A positive energy warp bubble, the mathematics reveals, cannot be created. Not because of an energy threshold you haven't reached, not because of a manufacturing precision you haven't achieved. It cannot be created because the only valid space-time histories in which such a bubble exists are histories in which it has always existed from before the Big Bang, drifting through eternity without beginning and without end, incapable of being switched on and equally incapable of being switched off. It is not a vehicle. It is a cosmic artifact, a permanent feature of space-time that no act of engineering or intention produced, and none can terminate. If one exists, it has been traveling forever. If one doesn't exist, no process starting from a normal initial state can bring it into being. The reason runs directly through causality. To activate a warp bubble from rest from a configuration of ordinary matter and energy sitting in ordinary flat space-time requires a sequence of physical operations. You arrange the energy distribution. You configure the field generators. You initiate the metric distortion. Each step in that sequence must be caused by the previous step. Information flows forward through the chain, but the full causal sequence required to build a superluminal warp bubble, when you trace it through the mathematics, demands that some information in the chain arrive at its destination before it was sent. The setup procedure for a superluminal bubble is itself superluminal. It requires its own conclusion to precede its own beginning. Picture trying to lift yourself off the ground by pulling upward on your own shoelaces. The mechanical logic is immediately clear. The force you apply through your hands is transmitted through the laces to your feet, which are attached to the same body you're trying to lift. Every component of the system is connected. Every action is real. The effort is genuine, and the result is precisely nothing, because the system has no external anchor. The action and its required precondition are the same object. There is no valid starting point. The warp bubble activation sequence is that problem. expressed in the language of spacetime geometry. The bubble needs to be there before you can build it. Building it requires it to already be there. The causal loop closes without ever opening. The universe doesn't refuse to cooperate. It simply has no coherent state in which the cooperation could begin. Solve the negative energy problem. The solution requires a bubble that predates the universe. Solve the instability problem. The control signals can't reach the wall. Solve the control problem. Arrival destroys the destination. Solve that the positive energy alternative was never buildable to begin with. Each solution spawns two problems. Each workaround closes one door and opens a wall. Is this a design flaw or is it a feature? Every time you solve a problem, the universe produces two new ones. That is either extraordinarily bad luck, or it is the universe being very deliberate about something. And that final layer doesn't arrive as a new problem. It comes from the very energy you use to build the bubble, which simultaneously acts as the fuse that destroys it the moment it takes shape. In 1974, Stephen Hawking published a result that nobody expected and almost nobody initially believed. Working through the mathematics of quantum field theory applied to the curved spacetime near a black hole's event horizon, he found that black holes are not perfectly black. They radiate. The intense space-time curvature at the horizon, the shearing gradient, where the geometry transitions sharply from flat space to the extreme curvature of the singularity tears virtual particle pairs out of the quantum vacuum. One particle of each pair falls inward past the horizon. The other escapes outward as real radiation. The black hole slowly loses mass. Given enough time, it evaporates entirely. 2 years later, in 1976, William Unruh independently derived a closely related result: an observer accelerating through flat spacetime with no gravitational field, no black hole nearby. Just ordinary empty space will detect thermal radiation that a stationary observer in the same location detects as nothing at all. The vacuum that appears empty to one observer appears warm to another, depending on their acceleration. The temperature of this Unruh radiation scales directly with the magnitude of the acceleration. The underlying mechanism is the same as Hawking's sharp gradients in the geometry of spacetime. Whether caused by gravity or by acceleration, interact with the quantum vacuum in ways that produce real physical radiation. Both results, Hawking radiation and Unruh radiation, share a single root cause. When the geometry of spacetime changes sharply enough across a short distance, the quantum vacuum cannot maintain its ground state uniformly across the gradient. It responds by producing particles. The steeper the gradient, the more energetic the response. Now consider the boundary of the Alcubierre warp bubble. The bubble wall is precisely a sharp gradient in spacetime geometry by design. The entire mechanism depends on it. Compressed space at the front, expanded space at the rear, and between them, a narrow transition region where the geometry changes radically over a very short distance. That transition region is, in the language of differential geometry, a region of extreme space-time curvature. It is exactly the kind of structure that Hawking and Unruh independently showed will interact catastrophically with the quantum vacuum. At superluminal bubble velocities, the space-time gradient at the bubble wall becomes steep enough to produce radiation analogous to Hawking radiation thermal, energetic, directed inward toward the spacecraft. This is not a speculative extrapolation. It follows directly from applying the same quantum field theory framework that produced Hawking's and Unruh's confirmed results to the metric Alcubierre specified. The bubble wall generates its own radiation field. That radiation field carries energy, and it deposits that energy at the boundary of the bubble, the very structure whose stability depends on maintaining a precise, delicate energy configuration. The energy used to create the bubble activates the mechanism that destroys it, not as a secondary effect that clever engineering might suppress. as a direct first-order consequence of the geometry. The builder and the destroyer are the same process, operating simultaneously. This is the universe functioning as what it has always functioned as. Underneath every layer of the analysis presented across these parts, a system that enforces causality with extraordinary thoroughness. And in 1992, Stephen Hawking gave that enforcement a name: the chronology protection conjecture. Published in Physical Review D, it states in Hawking's own framing that the laws of physics conspire to prevent the appearance of closed time-like curves, the technical term for causal loops that would allow information or matter to travel backward in time. His argument was that whenever a space-time configuration threatening to produce such a curve approaches viability, quantum effects at the relevant boundaries generate divergent energy momentum tensors, radiation, in plain language, that destroy the configuration before it can complete. The universe, he proposed, actively protects its own causal history. Hawking's tone when presenting this was characteristically dry. He noted that the conjecture was supported by what he called strong experimental evidence, namely, that history had not yet been disrupted by visitors from the future. The observation is wry, but the physics behind it is serious. Every structure that general relativity permits, and that would, if completed, allow superluminal information transfer or causal loop closure, wormholes held open long enough to become time machines, warp bubbles sustaining superluminal motion, appears to trigger quantum instabilities that prevent completion, not always through the same mechanism, sometimes through vacuum fluctuation amplification, as with the Finazzi-Liberati-Barceló instability result from 2009, sometimes through Hawking-type radiation at the boundary, sometimes through the causal impossibility of the initialization sequence itself. The specific mechanism varies. The outcome does not. Einstein's field equations are, as noted earlier, remarkably permissive. They accept wormholes, they accept warp bubbles, they accept, in certain exotic configurations, metrics that would function as time machines. These are all mathematically valid solutions, internally consistent, derivable, publishable, discussable. The equations do not refuse them. The equations are not the gatekeeper. Quantum mechanics is the gatekeeper. Every time a solution to the field equations threatens causality, every time a geometric configuration would, if realized, permit information to propagate backward in time or in a closed loop, quantum field theory appears with a mechanism that prevents the realization. The mechanisms are diverse, but the pattern is singular. It is as though the universe has a second set of rules, written not in the language of geometry, but in the language of quantum probability, and those rules consistently close every door that the geometric rules open. Hawking essentially said the universe has a terms of service agreement that nobody reads, buried somewhere in the quantum foundations of reality. The relevant clause, time travel, and its functional equivalents are not permitted. And unlike most terms of service agreements, this one is self-enforcing, automatically, universally, without exception or appeal. That's either deeply frustrating or deeply remarkable, depending on where you stand. But there is something stranger still waiting in all of this, something that flips the entire narrative, because the same rigid, unyielding rules preventing you from moving faster than light are also the reason you are here, thinking about moving faster than light. But here is the strangest thing of all: the rigid rules blocking us from moving faster than light are also the exact reason you exist to be frustrated by them. Rules feel like cages. That instinct runs so deep in human psychology that it barely needs examination. It simply operates, quietly, as a background assumption about what limits mean. A rule says no. A limit says stop. A boundary marks the edge of what's permitted, and everything beyond it belongs to the category of things you cannot have, cannot do, cannot reach. The emotional register attached to limits is almost universally negative. constraint, restriction, confinement. The story humanity tells about itself is specifically a story about breaking limits. Every chapter in the grand narrative of human achievement is framed this way. We crossed oceans that sailors once called the edge of the world. We built machines heavier than air and flew them. We left the atmosphere entirely, stood on another world, planted a flag in dust that had never known footsteps, and came home. Each of those moments is celebrated precisely because a limit was declared and then violated. The pattern is so consistent that it has become a template for how we understand progress itself. Limits exist to be surpassed. Boundaries are temporary. The impossible is just the not yet done. So when the speed of light emerges as a limit that cannot be crossed, a wall that the entire preceding analysis suggests is not merely tall but structurally infinite, the instinctive response is to frame it as failure, a ceiling humanity hasn't punched through yet, a humiliation dressed up in mathematics, evidence that the universe is larger than we are, more powerful than we are, indifferent to our ambitions. That framing is not just incomplete, it is precisely backwards. The same set of physical laws that prevents you from exceeding the speed of light is also the set of physical laws that produced you, not metaphorically, not inspirationally, literally, mechanically, at the level of electrons and chemical bonds and molecular folding sequences. The speed of light limit is not a separate rule imposed on top of an otherwise friendly universe. It is woven into the same fabric that holds every atom in your body together. Consider causality, the principle that causes precede effects, that information flows forward through time, that the sequence of physical events is ordered and consistent. Superluminal travel, as Part 2 established, would shatter causality. And causality is not merely a philosophical nicety. It is the operating condition for every chemical reaction that has ever occurred. A protein folds into its functional shape because the electromagnetic interactions between its constituent atoms proceed in a causal sequence, each atomic bond influencing the next in a chain that runs forward through time, producing a specific, reproducible three-dimensional structure. Disrupt the causal ordering of those interactions, and the protein does not fold incorrectly. It does not fold at all. The concept of folding into a shape requires time to have a direction. DNA replication works the same way. The polymerase enzyme reads the template strand in a specific direction, adds nucleotides in a specific sequence, and produces a complementary strand whose information content depends entirely on the causal ordering of each step. If the steps could occur in any order, if effects could precede causes, the information in DNA would be indistinguishable from random noise. Heredity collapses. Evolution has no substrate to work with. Life, in any form remotely resembling what exists on Earth, becomes impossible. The finite speed of light is what gives electromagnetic interactions their consistency across space. When one atom approaches another, the electromagnetic field carried by photons moving at the speed of light communicates the approach at a well-defined rate. Each atom responds to where the other atom was a calculable instant ago, and that slight delay is what makes atomic interactions predictable, reproducible, and capable of forming stable structures. If electromagnetic interactions propagated instantaneously, if the speed of light were infinite rather than finite, the mathematical structure of quantum electrodynamics, the theory describing how light and matter interact, would produce infinities everywhere. The calculations would break down. Chemistry as a coherent discipline would not exist. A finite speed of light is not a constraint on chemistry. It is a precondition for chemistry. The same applies to nuclear physics, to thermodynamics, to every layer of physical organization between subatomic particles and living organisms. Think of it this way. Every language has grammar, rules about word order, conjugation, agreement between subject and verb. Those rules limit what you can say. There are sentences that are grammatically impossible, constructions that the language refuses, orderings that produce nonsense rather than meaning. A speaker new to linguistic philosophy might experience grammar as a cage. All these things I cannot say, but strip away the grammar entirely, permit every possible arrangement of sounds with equal validity, and you do not gain freedom of expression. You lose expression altogether. Without rules, there is no sentence, no word, no meaning. There is only noise. The constraint is not the enemy of the message. The constraint is what makes the message possible. The laws of physics, including the speed of light limit, are the grammar of reality. They define what combinations of matter and energy produce stable structures, what sequences of events produce meaningful outcomes, what configurations of atoms produce molecules, cells, organisms, minds. Remove those rules make space-time freely and arbitrarily malleable. Let causality bend whenever a sufficiently advanced civilization decides it's inconvenient, and you do not get a universe where life travels freely among the stars. You get a universe where life cannot form at all, because the conditions for chemical and biological complexity require precisely the rigidity you removed. Every breath you take involves trillions of chemical reactions proceeding correctly, because space-time operates by rules that do not bend. Oxygen molecules bind to hemoglobin because electromagnetic interactions are consistent. ATP synthase rotates and produces energy because the causal sequence of molecular mechanics runs forward. Neurons fire in your brain right now because ion channels open and close in a causally ordered sequence that propagates electrochemical signals at speeds determined by the same electromagnetic constants that ultimately trace back to the finite speed of light. Every breath, every thought, every moment of awareness you have ever had, all of it runs on the same physics that prevents you from reaching Alpha Centauri in a human lifetime. Do you want the universe to break those rules so you can get there faster? And if those rules are the foundation of life itself, then the question is no longer, why does the universe imprison us? But where exactly are we standing in a universe we cannot leave? The same universe that built you also built a barrier you cannot cross. That is the paradox sitting at the center of everything in this story, and it does not resolve cleanly into either triumph or tragedy. It simply sits there, enormous and patient, demanding to be looked at directly. The observable universe spans approximately 93 billion light-years in diameter. Within that volume, a 2016 study published in the Astrophysical Journal by Christopher Consolis and colleagues, using deep field observations from the Hubble Space Telescope combined with mathematical modeling of galaxy evolution, estimated the total number of galaxies at approximately 2 trillion 2 million millions each, containing hundreds of billions of stars. Each star potentially accompanied by planets. Each planet potentially harboring conditions where chemistry grows complicated enough to become interesting. 2 trillion galaxies. The number is large enough that human intuition abandons it entirely. It becomes an abstraction, a figure that exists only as text on a page, impossible to feel or visualize or relate to anything experienced in an ordinary life. And almost none of it is accessible to us. Not with current technology, not with any technology permitted by the physics described across these parts, not ever, because expansion is accelerating and the horizon is shrinking. Even traveling at the speed of light, which Part 1 and Part 2 established, is physically impossible. For matter, the nearest large galaxy, Andromeda, sits 2.5 million light-years away. A journey at the speed of light would take 2.5 million years. Homo sapiens as a species has existed for approximately 300,000 years. The entirety of human history, from the first stone tools to the James Webb Space Telescope, fits inside a span of time roughly 12% as long as the journey to our nearest galactic neighbor, moving at the maximum speed the universe permits. at any velocity a spacecraft could realistically achieve. That journey takes not millions of years, but billions. The universe shows it to us. That is the part that stops the mind if you let it. The James Webb Space Telescope has captured light from a galaxy designated JADES-GS-Z13-0, located approximately 13.4 billion light-years away. The light that formed that image left its source when the universe was approximately 400 million years old, a time so early in cosmic history that the structures we recognize today, the galaxies, the stellar populations, the chemical elements heavier than helium, were only beginning to form. Webb's instruments collected that light, focused it, resolved it into a smear of infrared photons, and produced an image that humans can look at on a screen. But what is that image? Really, it is a fossil. A photon fossil, the imprint of light that has been traveling for 13.4 billion years, carrying information about a source that may look entirely different today, that may have merged with other galaxies, that may have exhausted its star-forming gas, that may host civilizations who have risen and fallen 1,000 times in the interval since that light departed. We are not seeing that galaxy. We are seeing its past. The universe is transparent to us only in the way that history is transparent. We can read it, study it, reconstruct it, but we cannot touch it and we cannot change it. Every telescope is a time machine running in one direction only, and it never moves. This could be read as desolation. The universe as an exhibit behind glass, infinitely large and infinitely remote, showing us wonders we can document but never visit. The loneliness implicit in that picture, 2 trillion galaxies visible and essentially none of them reachable, is genuine. It is not a feeling to be dismissed with forced optimism or distracted away by the next interesting fact. But there is another way to hold it, one that requires stepping back far enough to see the full shape of what has actually happened. A species of bipedal mammals, averaging 1.7 meters in height, evolved on a moderately sized rocky planet orbiting an unremarkable star in the outer arm of one galaxy among 2 trillion. This species existed for 300,000 years, a geological eye blink, a rounding error in cosmic timekeeping. In the final fraction of that span, roughly the last few thousand years and accelerating sharply in the last few hundred, this species developed the capacity to measure the universe, not visit it, measure it. They determined the diameter of the observable universe to within a few percent. They measured the rate of its expansion and discovered that the expansion is accelerating. They mapped the distribution of 2 trillion galaxies using instruments attached to telescopes in orbit. They worked out the physics of what happened in the first fractions of the first second after the Big Bang. They identified why they cannot travel faster than light, and they did so correctly, rigorously, using mathematics that has been verified experimentally to extraordinary precision. They cannot go there, but they know it is there. They know the distance, the velocity, the temperature of the gas between the stars, the chemical composition of galaxies they will never approach. They know why the distance is permanent, and they know what would have to change about the structure of reality for it not to be. We cannot go there, but we know it is there. We know the distance. We know the speed. We know the temperature. Has any other species in the 3 billion year history of life on Earth ever done anything remotely like that? Humanity cannot exceed the speed of light, cannot leave the solar system with current technology, and for that matter, cannot seem to agree on a single time standard across its own planet. But it has measured the size of the universe using mathematics. That is, by any reasonable accounting, one of the strangest and most beautiful things that has ever happened on this small rock. We are genuinely bizarre, in the most wonderful way possible. The answer to that question doesn't live in a new engine design or a new equation. It lives in something the scientific community only recently, in the year 2024, found the courage to acknowledge publicly. The math allows it. The universe resists it. That phrase has followed every single part of this story, like a shadow. Alcubierre wrote the geometry down correctly. The equations didn't break. No internal contradiction appeared on the page. And yet, every time physics tried to turn that geometry into something real, something physical, something buildable, something you could actually climb inside and point toward a star, the universe produced a new mechanism of resistance, negative energy requirements, quantum inequalities, event horizon blindness, gamma ray detonation at arrival, causal initialization loops that close before they open, Hawking-type radiation eating the bubble wall from the inside out. The math kept saying yes. The universe kept saying no. Every single time. The naive interpretation is that the universe is stubborn, hostile, that it built a cage and threw away the key, and the whole exercise of theoretical physics is just increasingly sophisticated rattling of the bars. But that interpretation misses something fundamental. Something that the pattern itself is trying to tell us, if you're willing to hear it. When mathematics and physical reality systematically disagree, that disagreement is not evidence of the universe's bad faith. It is evidence that the mathematics is incomplete, not wrong incomplete. Einstein's field equations, written in 1915, describe the geometry of spacetime with extraordinary precision within their domain. Quantum mechanics, developed through the 1920s and refined for a century since, describes the behavior of matter and energy at the smallest scales with a precision that rivals anything in the history of science. Both frameworks are correct. Both frameworks are verified experimentally to decimal places that make engineering tolerances look sloppy by comparison. And they do not fit together. That is the largest open problem in theoretical physics, not the largest unsolved problem in warp drive research. The largest unsolved problem in all of physics, full stop. The incompatibility between general relativity and quantum mechanics is not a footnote. It is the central wound in the body of modern science, a gap that has resisted every attempt at closure for 100 years, that has consumed the careers of some of the most brilliant minds the species has produced. And that remains as open today as it was when the two frameworks were first recognized as fundamentally incompatible. Every time the warp bubble encounters a quantum mechanical objection, the Ford-Roman inequalities, the Hawking-type radiation, the vacuum instability, it is encountering a symptom of that wound. The resistance isn't arbitrary. It is the sound of two incomplete pictures of reality colliding at the boundary of what each one can describe. The theory that would resolve this quantum gravity, the framework that would unify general relativity's description of curved spacetime with quantum mechanics' description of discrete, probabilistic particle interactions does not exist yet, not in a complete form. String theory is a candidate. Loop quantum gravity is a candidate. Several other approaches have been proposed, explored, and found to be promising in some respects and insufficient in others. None of them have produced a full, testable, experimentally confirmed theory of quantum gravity. That theory remains the destination of a journey that hasn't ended. What quantum gravity, when it arrives, will do to the warp drive question is genuinely unknown. It could close every door that this analysis has examined, confirm that the quantum mechanical resistance is not a series of solvable obstacles, but a unified prohibition written into the deep structure of reality at a level Einstein's equations simply cannot see. Or it could open something entirely new. A quantum gravitational description of spacetime might reveal geometrical possibilities that neither framework alone can describe, structures that satisfy both the relativistic requirements for superluminal motion and the quantum requirements for stability, causality, and energy conservation. Nobody knows. That is not a comfortable answer. It is an honest one. In April of 2024, Alexei Bobrik and Gianni Martire, the same researchers whose 2021 paper had documented the gamma-ray weapon problem at arrival, published something different. Not a new warp drive design, not a proposed solution to the negative energy problem. Something more methodical, and in its own way, more significant, a comprehensive classification framework for all possible warp metric solutions to Einstein's field equations. What Bobrik and Martyr built in their applied physics paper was a map, not a map of space, a map of the solution space itself, a systematic taxonomy of every category of space-time geometry that could, in principle, produce apparent superluminal motion, organized according to which energy conditions each solution satisfies or violates, which physical constraints each respects or breaks, and where each one sits in relation to the known obstacles. The framework doesn't tell you how to build a warp drive. It tells you, for any proposed warp metric, exactly what it would require, what it would violate, and what class of problems you would need to solve to make it physically realizable. The significance of that is easy to underestimate. Before this framework existed, every proposed warp solution was evaluated in isolation. Someone would write down a metric, trace its implications, discover a problem, and either abandon it or attempt a fix. The process was uncoordinated. There was no shared vocabulary for categorizing proposals, no systematic way to determine whether a new idea was genuinely novel or a variation on a previously examined dead end. No method for mapping the boundaries of what remained unexplored versus what had already been shown to fail. Warp drive research was a field of individual expeditions into unmapped territory, each one returning with partial information that nobody had yet organized into a coherent picture. Bobrik and Martyr drew the map. For the first time, the scientific community has a framework for knowing what it doesn't know, a structured picture of the solution space that distinguishes the regions already explored from the regions not yet examined, the categories of solutions already ruled out from the categories that remain open. No one is claiming the destination has been found. What they built is the cartography of the search itself. That is not a small thing. It is what a field of research looks like when it matures. The history of science is full of moments when a discipline shifted from scattered individual efforts to a systematic program, when the questions became organized enough that progress could be measured and coordinated rather than stumbled upon. Warp drive research, for all its extraordinary theoretical difficulty, has reached that inflection point. The map exists. The expedition can proceed with some sense of what it's actually looking for. You're waiting for a verdict, possible or impossible, yes or no, the kind of clean answer that a video like this is supposed to deliver, the conclusion that wraps everything into a position you can carry forward into the next conversation you have about interstellar travel. The honest answer is that the verdict isn't in, not because the physics is poorly understood. It is understood with remarkable depth and precision, as everything across these parts has demonstrated. Not because scientists haven't looked hard enough. They have looked very hard. For decades, with the best mathematical tools the species has built. The verdict isn't in because the question turns out to be deeper than anyone realized when Alcubierre first published his paper in 1994. The resistance the universe offers isn't the resistance of a solvable engineering problem. It's the resistance of a framework collision to correct but incomplete pictures of reality, pushing against each other at the boundary of the unknown. The right question was never whether we could get there. The right question, the one that actually points somewhere useful, is whether we have the courage to keep asking. And perhaps that is the greatest legacy Alcubierre, Einstein, and Hawking actually left behind, not the answer, but the art of asking the right question in the right place. Step all the way back, take in the full shape of the journey. Newton's rocket, Einstein's curves, Alcubierre's bubble, the Ford-Roman quantum inequalities, Hawking radiation eating the bubble wall. the causal loop that closes before it opens. Every step forward in this story revealed not a solution, but a deeper layer of the problem. Not a cleaner answer, but a stranger, more demanding question waiting underneath. That is not failure. That is what genuine inquiry actually looks like from the inside. Progress in physics has never felt like arriving. It has always felt like discovering that the room you just entered is larger than the building you thought contained it. Humanity sits in a genuinely strange position right now. Strange enough that it's worth saying plainly. We are intelligent enough to understand that we cannot get there, and we are intelligent enough to know, with precision and rigor, exactly why. That combination, knowing the limit and knowing its cause, has never existed before in the 300,000-year history of this species. For most of human existence, the stars were simply unreachable. The way the bottom of the ocean was unreachable. The way the inside of an atom was unreachable, remote. Mysterious, beyond the tools at hand. Now the stars are still unreachable, and we can write down the equations that explain why, verify them experimentally, and trace the resistance back to a collision between two incomplete but correct pictures of reality. That is a different kind of knowing. Harder in some ways, more honest in all of them. Quantum gravity remains unfinished. When it is finished, and it will be, because the question is too central to the structure of physics for it to stay open forever, everything in this video may need to be revised. Every door the analysis closed might reopen. Every door it left open might close. The theory that unifies general relativity and quantum mechanics will not merely adjust the warp drive calculation. It will rewrite the vocabulary in which the question is asked. What we know now is not the final answer. It is the current edge of the map. And the only certain thing, at that edge, is this: what we do not know is vastly larger than what we do. That is not a reason for grief. It is the only reason to continue. The speed of light limit is not the final wall. It is writing on a wall, and the writing says that there is a room on the other side that we do not yet have the language to describe. Every Cassini probe threading between Saturn's rings, every James Webb image pulling light from 13 billion years ago, every LIGO detection of gravitational waves from colliding black holes, none of it was built to conquer the universe. All of it was built to listen, to catch what the universe says when it thinks no one is paying attention. The warp drive question does not end at impossible. It ends at not yet understood why. And that distance between the known limit and the unknown reason behind it is the farthest, most alive territory that human intelligence has ever tried to enter. The universe is 13.8 billion years old. Humanity is 300,000 years old. Modern physics is 100 years old. We have barely begun to ask. Whatever the answer turns out to be, whether it closes every door or opens one we never imagined, it will not come from a single genius working alone in a quiet room. It will come from the people who refuse to stop asking, the ones who sit with the silence the universe returns, who find in that silence not an ending, but a direction, and who keep building the questions even when the answers don't come. The universe is patient. It has been keeping its secrets for 13.8 billion years. We have only just started knocking.